Hello and welcome to this video lecture. Today's lecture will be on the topic of rocket basics. As with our previous video lectures and PowerPoints, the original PowerPoint was put together by Eric Smith, but I have made some updates to account for more recent information. And today's video lecture is brought to you by Bill Kerbel of the Kerbal Space Program. So the introduction will cover in this particular lecture the topics of our rocket model that we introduced in the projectile motion lecture. We'll then discuss the topic of calculating the thrust to weight ratio and what the implications are for the value for different types of rockets. We'll then take that quantity and use it to calculate the initial acceleration of the rocket at liftoff. Other considerations that should go into our ultimate rocket model will be addressed at this point, but we will not go into much detail regarding them. And after we discuss the effects of the thrust to weight ratio, we'll then turn our attention to the question of the stability of our rocket. We'll address the factors that go into determining whether a rocket in flight is mechanically stable or not. The two most important quantities for us to consider are the location of the center of gravity of our rocket, or the center of mass, as well as where the center of pressure is applied on the rocket frame. We'll discuss the elements involved in determining whether a particular rocket is stable or unstable. And then we'll discuss some of the ways we can optimize the stability of a rocket and finish out with a discussion of how we evaluate the stability of larger rockets that are capable of adjusting their engine nozzles to engage thrust in various directions. So in the previous segment on projectile motion, we had introduced a very basic model for the flight of a rocket. We used the projectile that is moving upward as well as horizontally. It traced out a parabolic trajectory above the ground, and then it returned to the ground at some later point. Now, a real rocket, of course, is a number of additional factors that need to be considered. So in order to better understand the physics that we are working with, we're going to build a more sophisticated mathematical model of the situation. In the following model, the arrows are going to represent various types of force vectors. These arrows are going to show both the direction and the magnitude of the different forces involved. And in this level of the model, we will only be considering two forces. There is the force of gravity, which is pointing downward, and that corresponds to the weight of the rocket. And then there is the thrust, which points upward, as shown in the green arrow. And the net force acting on the rocket is then the difference in those two forces here. If we were to draw a thrust vector that is shorter than the weight vector, the resultant will be pointing down like this. And if that is the case, you do not have enough thrust to actually get launched off the pad, and you're stuck there. If, however, we have a situation where the thrust is a larger force pointing upward, then the resulting force is going to point upward, and that is what you need to achieve liftoff. So the key then to determining if a given rocket can lift off of the pad is comparing the thrust of the rocket's engines to the overall weight of the rocket. So if we can calculate both that weight and the thrust of the rocket, we then can determine if we'll be able to lift off. So we know that the force of gravity is given by this expression. This is basically Newton's second law. with the force being gravity in this case. So the force is equal to the mass times the acceleration, and the acceleration due to gravity is identified with a lowercase letter g. And so m represents the total mass, and g would represent the local gravitational acceleration. And since we will be on a launch pad based on the surface of the Earth, the value we will use for g in that situation is the value for the Earth's gravitational acceleration, which is 9.81 meters per second squared. Now, in this formula, if you then give the mass in units of kilograms, then the weight or the gravitational force associated with the rocket is given in units of newtons. So that is the weight part of the calculation. The other half is the thrust. The thrust for different rocket engines is given by the specific engine being used. Oftentimes with a model rocket, you have a 3-digit code that gives you the information regarding the properties of that model rocket engine. Here is a summary of the kind of information that code is associated with. So the code begins with a letter like A, B, C, or D, and that represents what's known as the total impulse or power that will be produced by that engine. The next number is what we'll be interested in for this lecture. That is going to be the force that the engine gives off on average in units of newtons. The third number is the amount of time it takes after the engine finishes its burnout until the ejection charge deploys the parachute and the nose cone is separated from the body of the rocket. So a longer delay time there means a later ejection of the nose cone and deployment of the parachute. So you don't want to wait too much because you may be all the way back on the ground before the ejection charge operates. But for our purposes, again, for this lecture on rocket basics, the number we are going to be interested in is the second number, which represents the force in newtons that is generated by the rocket's thrust. So if you know both the thrust and the weight of your rocket, you can then calculate a ratio of those two quantities, what's known as the thrust to weight ratio, or TWR. Basically, it's very simple. The numerator is the thrust force in newtons. The denominator is the weight force in newtons. So that's simply your thrust divided by the mass times g. And the ratio will have one of 3 ranges of values. The first possibility is that the thrust to weight ratio will be less than 1. If it is less than 1, that means that you have the situation we showed earlier where the resulting net force was pointing downward. And that means you will not launch. You don't have enough thrust to overcome just the weight of the rocket itself. A second possibility would be that the thrust to weight ratio is exactly equal to 1. In this situation, what that means is that the net force between these two oppositely directed forces would be 0. You'd have as much upward force from the rocket thrust as you would have downward force from the weight of the rocket. And if the force is 0, there will be no acceleration. Basically, what you're talking about there is that the rocket may hover right on the launch pad, but it will not go upward. In order to actually successfully lift off, you need a thrust to weight ratio that is greater than 1, and that will achieve liftoff. So let's look at a couple of examples of how you calculate this thrust to weight ratio. In the case of a model rocket, let us consider using an engine that is designated as B6-2. The 6 means that the thrust of the engine will be 6 newtons. Let us further assume that the mass of our rocket is all of 50 grams, which is just a couple of ounces. That corresponds to 0.05 kilograms. All right. And again, the gravitational acceleration is 9.81 meters per second squared. So if we apply our formula for the thrust to weight ratio, the numerator is 6 for 6 newtons. The denominator is 0.05 kilograms times 9.8 or 9.81 meters per second squared for little g. When you plug those numbers in, you'll get a thrust to weight ratio of about 12, which is why a model rocket very typically takes off rather rapidly upon the ignition of the rocket engine. It has a very high thrust to weight ratio. As an alternative example, sort of at the opposite end of the spectrum of rockets, the largest rocket that the United States has ever launched, and possibly the largest rocket that has ever been launched, has been the Saturn V. The Saturn V was a multi-stage rocket. The first stage had 5 Rocketdyne F1 engines that were each capable of generating a thrust of 6,770.1933 kilonewtons. That's thousands of newtons. And that's from each of those 5 engines. The mass, when fully fueled, of the Saturn V was 2,800 metric tons, where 1 metric ton is the same as 1,000 kilograms. So that's 2.8 million kilograms of mass when fully fueled on the launch pad. Again, the gravitational acceleration, little g, will be 9.81 meters per second squared. And so we plug these values into our formula for the thrust to weight ratio. We have 5 separate engines that each generate that force, that thrust listed above. And we have 2,800 tons that is associated with the weight of the rocket. You'll notice that I don't use the 2.8 million kilograms in the denominator, nor do I use the 6,770,000 newtons in the numerator. The reason why is that the factor of 1,000 in the numerator cancels out the factor of 1,000 in the denominator, so we don't have to worry about that. We plug these numbers in to our calculator, and we get a thrust to weight ratio of roughly 1.25. And if you remember ever watching some of that file archival footage of the launches of a Saturn V, you'll note that at the very start, when the rocket engines are first ignited, the rocket lifts off pretty slowly. And that's because the thrust to weight ratio is only a little bit larger than 1, rather than the rapid launch that we'll see for our model rockets on Monday. So another factor we can consider is what is that initial acceleration off the launch pad. By knowing our thrust to weight ratio, we can calculate this value. So the process of deriving the formula for the initial acceleration is shown as follows. We start with Newton's second law, F equals ma, where F is your net force upward, which is the difference in your thrust and your weight. So we can replace the net force with the thrust minus the weight, or the gravitational force, is equal to ma. We can then divide both sides by the mass of the rocket and get this equation. From here, we'll just flip the order, so we'll put the a to the left side of the equals and the other expression on the right side. Next, we will convert the gravitational force into its weight simply as being m times g. Then we will split the numerator up into 2 separate terms. So we have the thrust divided by the mass minus the weight divided by the mass. And then we can simplify the second term because the mass will divide out. And that just leaves you with the factor of g. The next step in our derivation here is to multiply the first fraction in both its numerator and its denominator by this factor of g. And you'll see why we do that in a moment. Now what we have is two terms. In the numerator of the first term is a factor of g, and in the second term we have a factor of g. We could factor that out of both of those terms, and that would give us g times the expression, the thrust divided by m times g minus 1. M times g, of course, is just the weight. So that first term there is your thrust divided by the weight, or your thrust to weight ratio. And so we finish out our derivation by noting that the acceleration initially upon liftoff is the gravitational acceleration of your planet or moon times the thrust to weight ratio minus 1. So when we had an example of the model rocket, we had the B6-2 solid engine that generated 6 newtons of thrust. It had a mass of 50 grams or 0.05 kilograms, and the gravitational acceleration was 9.81 meters per second squared. With these numbers, we showed the thrust to weight ratio was 12.24. So if we plug that value into this equation for the initial acceleration, we get the value of about 110 meters per second squared. And that is why a model rocket launches so rapidly. It's mostly because the weight of a model rocket is usually pretty low, a few dozen grams at most typically. So this model we have generated of a rocket with an engine that is actively generating thrust still has a number of simplifications. There are a number of other considerations we can put into our model, and as time progresses, we will be adding more of this into the overall picture of how a rocket engine and our rocket works. Rockets usually come with multiple engines, specifically big rockets. They have multiple stages. The engines themselves can be throttled at different percentage of maximum thrust. And they can travel in more than one direction because you can swivel them. So more than one engine means that when you calculate the total thrust of the rocket, it will be the total thrust of all of the engines that are actively generating propulsion. So if it's a multi-stage rocket, only those engines of an associated stage are active at any given time. So those are the only ones that will contribute to the thrust. So the first stage engines during the initial phase of a launch are the ones that contribute to the thrust. Second stage engines, once the first stage is terminated and the first stage part of the rocket has been detached, that will reduce the total weight of your rocket as you go to subsequent stages. So that's another factor that needs to be considered in terms of evaluating accelerations and so on. The ability to increase or decrease the thrust of a liquid rocket engine is a very useful property as well. The percentage of the full throttle being applied can then be multiplied by that maximum thrust of those engines. Other considerations as well, the formulas we've given for thrust to weight ratio and for initial acceleration provide us a great snapshot of what you can expect primarily at the moment of liftoff. But as the rocket is flying, you're dealing with a system that is highly dynamic. Different quantities are changing all the time. You're getting a changing amount of air pressure, as we'll discuss in a moment. You're getting a changing total mass of the rocket because you are burning fuel. So that means the mass of the rocket will decrease. In addition, the further away you get from the surface of the world you're launching from, the Earth, for example, the lower the gravitational acceleration becomes because you're further away from the source of the gravity. And also notable is that if you're launching off the surface of a world with an atmosphere, that atmosphere is going to slow you down due to air drag. That is another force we have not yet considered, and how much it will slow you down will depend on a number of factors, but most especially, it depends on where you are in the atmosphere. The lower you are, the thicker and denser the air will be, and hence the more effect the air drag will have. It also depends on how fast you are going. When you're moving slowly, air drag is not that major an effect. But as you speed up, it becomes quite important in the overall dynamics of the rocket launch. But at the same time, the faster you're going, the higher up you are, the thinner the air gets. So there are competing factors to take into account there. So that's a little bit about the relationship between the thrust generated by a rocket engine and the weight of the rocket and how that affects the initial flight dynamics as the rocket is lifting off of the pad. Another factor that we wish to incorporate into our model of the rocket is we want to make sure that the rocket remains stable in its flight. But what exactly do we mean by a stable rocket? We're going to look at a few situations in order to see if we can develop the idea of stability, and from that we'll then apply it to our rocket model. So to pursue that, we will need to introduce a few new terms, some vocabulary. So to understand the concept of stability, let us consider we have a ball found in a round bowl. Note that if the ball is at the bottom of the bowl, what's known as the neutral position, it won't roll anywhere. It will just sit there. However, if you were to displace the ball from that neutral position, what would you expect it to do? If you think about it for a moment, in this situation, you would expect the ball to roll back down towards the neutral position, and ultimately, as a consequence of forces like friction, the ball will return to the neutral position. So anytime you have an object that is displaced from the neutral position and it has a tendency to return to that original position, we say that that is a stable object. So stability is a tendency to go back to the neutral position instead of moving away from the neutral position. So if we wanted to consider the opposite situation in this same analogy, the way we would do that is we would take the bowl and flip it over. If we did that, then the neutral position would be where the ball is on the top of the bowl. But you can imagine what would happen if that ball is displaced even slightly away from the neutral position. If that were the case, the ball will continue to move further away from the neutral position and roll off of the bowl. And anytime an object moves away from its neutral position after it has been displaced, that is said to be an unstable object. So stability is the tendency to return to a neutral position, and instability is the tendency to move away from that neutral position. So how do we apply these ideas to a rocket that is in flight? If a rocket is in flight, if it's flying straight up, it is flying through an atmosphere in this particular example. The air is basically flowing away, down. in the opposite direction to the flight of the rocket. And as long as the rocket is flying straight up, it is in its neutral position. If the rocket were to slightly tilt in one direction or another, that would displace it from the neutral position. Here you'll note it's not a translational motion, but rather a rotational motion that causes this displacement. And the question of stability is essentially a question of whether or not that displaced rocket will tend to go back to its neutral position, as shown here, which would be stable motion, or if it would tend to rotate away from that neutral position, which would be unstable motion. So what we're looking for then are rockets that will maintain their stability, that will have a tendency in flight to return to that neutral position. And as we just noted, what that means is we have to consider how the rocket will rotate based on aerodynamic forces applied to it in flight. Now, a good rule of thumb for a rocket, if the engines cannot be vectored or swiveled into different directions, is that you want to make sure that a location on the rocket called the center of pressure is found either behind or below the center of gravity of the rocket. So let's see why this happens to be the case. The center of gravity can be thought of as the balance point of a rocket. A good analogy for what the center of gravity or the center of mass of a system would be is a playground seesaw. That if you have equal masses at equal distances from the pivot point of a seesaw, then you can achieve a balance where the seesaw does not tip in one direction or another. So the center of gravity of a rocket would be that particular location where basically half of the mass roughly is on one side and the other half is on the other. And I say roughly because it also depends on how that mass is distributed. The center of gravity is very important for stability calculations because it turns out a rotating rocket only rotates around that particular point on its body. It cannot rotate around the nose cone or around the rocket engines. It rotates around the center of gravity. So if you wish to find the location of the center of gravity on your model rocket, for example, one way to do that would be to take your model rocket and try and balance it on the edge of a ruler. I would do this with the engine actually in the rocket because that will help to identify the center of gravity at the point where the rocket is launched. But basically, you want to find the point where the rocket does not rotate one way or the other when you put it on a very narrow edge like your fingertips or on a ruler edge. The reason why the rocket would rotate around that point is because there are forces that push on the rocket unevenly around the center of gravity. So if there is more force on one side of that center of gravity than on another, that will cause the rocket to rotate or spin from the greater force on the one side. And so the important factors for the stability of the rocket then are how far away from the center of gravity are the forces applied and how much force is being applied, and whether or not the tendency for the rotation would be to return it to its neutral position or move it further away. So the force that will affect the flight and the rotation of the rocket is the aerodynamic force of flying through the atmosphere. And where that force is centered on the rocket is the point known as the center of pressure. That center of pressure is basically the center of the air pressure forces acting on the rocket when it is flying. So we've indicated the center of pressure here with a circle with a dot in the middle of it. The aerodynamic forces, the pressure forces, act on a line that is perpendicular to the center line of the rocket shown by my cursor, moving back and forth. So they're pushing inward on the rocket, and that's just due to air pressure. So if you wish to locate the center of pressure for your rocket, one way you could do that would be to create a cardboard cutout of your rocket silhouette. The center of pressure only depends on the layout and the area of the side of the rocket, the lateral area. And the point where it is centered is basically the area center, as opposed to the weight center that the center of gravity represents. So if you were to create such a silhouette, you would then find the balance point of that silhouette, and that is roughly the center of the lateral area, which is roughly a good approximation for the center of pressure if we launch our rocket straight up at an angle of 90 degrees. So in order to establish stability, what we want then, a good rule of thumb for our rocket, where you cannot vector the direction of the engines, is to make sure that the location of the center of pressure is found behind the center of gravity or below it, closer to the rocket end of the rocket, or the engine, I should say, and the center of gravity would be closer to the nose cone end of your rocket. So given the two centers that we're discussing here, we could show how they work together in order to create a stable rocket flight, and show why if they were flipped in their positions, that would lead to an unstable flight. So keep in mind, the rocket will always rotate around its center of gravity. So here we have our silhouette of a model rocket. The center of gravity is marked. The center of pressure, in the case of a stable rocket, is below or behind the center of gravity. And that indicates the location where the aerodynamic forces acting on the rocket will be applied. So we've indicated the aerodynamic forces of a rocket that is in flight, going up through the atmosphere. If the rocket starts to tilt in one direction or another away from its neutral position, then you'll find that there will be more pressure on one side of the rocket than on the other. In this instance, the way the rocket is tilted, there will be more pressure on the right side of the rocket. And if that is the case, it will push more on the rocket to the left, and that push is applied at the center of pressure, as indicated by the purple arrow pointing to the left. And you'll notice that if the rocket has to rotate around its center of gravity, and it has a force acting in that position to the left, the tendency of the rocket will be to rotate like this, clockwise in this orientation. And in this situation, that means the rocket will turn back into its neutral position. So this is the stable configuration. Conversely, if our rocket had a center of pressure that was located above or in front of our center of gravity, we'll find that that results in a different type of stability. So here the center of pressure is indicated up here, and the center of gravity now is over here. Once again, flying through the atmosphere, the pressure from the aerodynamic forces pushing on the rocket will tend to push it to the left at the center of pressure. So we apply that force at that point, but now rotating around the center of gravity, that would cause the rocket to rotate in the counterclockwise direction. And given that that would force it to move further away from the neutral position, this is what gives rise to the instability. And so the goal then is you want to make sure that your center of gravity is above or in front of your center of pressure. And the further you move the center of pressure away from the center of gravity, the easier it will be for your rocket to maintain its neutral position if it were to start to be displaced from it. And a good rule of thumb in this situation, in order to achieve a good degree of stability, would be to make sure that the minimum distance between the two centers of gravity and of pressure would be at least as big as the largest diameter of the rocket. So if your rocket is a model rocket that is, say, 2 centimeters or 3 centimeters wide for the tube, then you'd want your center of pressure to be 2 or 3 centimeters behind your center of gravity to maximize that stability. Other considerations, let's think about some of the effects that would happen. So suppose we have a stable rocket that has an engine with fuel and all the other supporting structures to determine where the center of gravity and where the center of pressure are located. If we were to swap out that engine for a larger, heavier engine, that would mean that you'd have more weight at the back end of the rocket, and that would change the location of your center of gravity. Now the question is, does that make the stability greater or less if you did that? And if you think about it for a moment, if you're moving the center of gravity closer to the back end of the rocket, that actually decreases your stability. It makes it easier for the rocket to become unstable. Another factor, as we previously noted, as your rocket is firing, it will be consuming and burning up fuel and expelling the propellant out the back end, and that will also cause the center of gravity to move, because in this case, the location where the propellant is located, usually in fuel tanks or for our model rockets within the casing of the rocket engine itself, that's located at the back end of our rockets typically. If you're losing mass at the back end, then the center of gravity will move, but which direction do you think it will move? Again, here is our stable rocket. The center of pressure is behind the center of gravity, and as the rocket is flying and it's burning fuel, it loses mass on this side, and hence this side becomes effectively heavier, and the direction the center of gravity will move in this instance will be to the right. And if that's the case, it will make the flight more stable because you're moving further away from that center of pressure, and it is further behind the center of mass. So that would be good in terms of the rocket's overall stability. So other considerations as well, as you are gaining speed and altitude, the faster you move through the atmosphere, the greater will be the force that acts on the center of pressure. So what effect would that have if we are moving at a steeper angle? Consider that when the rocket is basically vertical, the pressure on both the left and right hand sides is essentially equal. And so there's no net force acting at the center of pressure to cause the rocket to rotate. But as the rocket becomes more and more steep in its flight angle, one side of the rocket will encounter more pressure, the other side will encounter less pressure, and the steeper the angle, the greater that disparity, and hence the stronger will become the force acting at the center of pressure. So at a steeper angle, you'll get a larger force, indicated here with a longer vector. And again, with this configuration, that force will tend to cause the rocket to rotate clockwise, which will tend to bring it back up to its neutral position. So we'll finish out with a very brief discussion of what you do with bigger rockets, professional, commercial rockets, the types of rockets that are launched by space agencies like NASA or Russia or China or the Europeans. We now know about the center of pressure and the center of gravity. We understand why they are very important in the case of a situation where your rocket engines cannot be vectored, cannot change the direction of thrust. So bigger rockets basically account for the potential instability they encounter by allowing their engines to swivel in order to change the thrust vector and allow the rocket to maintain its neutral position. But despite this, the rockets will still tend to rotate around their center of gravity, so they still have to be very careful in designing the launch trajectory to ensure that they can successfully get to orbit. So we will finish out this particular topic with an online activity for each of you to complete this week. The activity will be due again at Sunday night at midnight. It's a fairly straightforward activity. What I want each of you to do is to go onto your computers and look up a rocket online, either a rocket that is deployed by NASA or from some other launch agency. It could be one of the current crop of new rockets that are coming on from commercial space ventures like SpaceX or Blue Origin. Look, one could be a current rocket, it could be a former rocket, it could be the Saturn V, for example. What you want to do is you want to record the thrust of that rocket in newtons. And in the case of a multi-stage rocket, which many of these rockets will be, you only want to consider the first stage total thrust of the engines in that case. You also want to record the mass of your rocket in kilograms, including the mass of the fuel when it is fully fueled. You do not want to record the dry mass of the rocket. And using the online rocket calculator you will find on Blackboard in the handout in the class document folder, you want to determine both the thrust to weight ratio of your rocket as well as its initial acceleration. And then submit that in the Excel file with those numbers entered to show your values. All right. So I'm going to show you a brief example of how to find that information for a particular rocket, apply it to this calculator, and determine the results. So what I have here, let's first do a little research. I chose the SpaceX Falcon Heavy rocket, and I did a Wikipedia search for that. Well, I did a Google search for that and found the Wikipedia page. And in this particular case, if I scroll down the Wikipedia page, I get down here to the rocket specifications. And very conveniently, they give me the information I need. They tell me the total mass when fueled up is 433.1 metric tons, or 955,000 pounds, but we're not interested in the mass in pounds. And it also tells me the thrust for each stage. The first stage, the thrust for the total stage. For the first stage, my total thrust in newtons is 22.82 meganewtons, MNs. Those are millions of newtons. And so what I can do is I can take the rocket calculator. Note that this Excel file was designed by Mr. Smith, and he provided the ability to change the origin of where you're lifting off from. Here, if you wanted to change it to any of the fun little worlds from the Kerbal Space Program, they've got several of those worlds listed, as well as the Earth, Moon, Mars, and Venus. For our purposes, we'll just use the Earth. The thrust force that we found for the rocket, again, the stage total thrust, 22.82 meganewtons. All right. So in here, I would enter 22,820,000 newtons, or the units given here are kilonewtons, so 22,820. If you have trouble converting between megas and kilos and just straight up newtons, remember it's all based on factors of 1,000. So it's just a matter of moving the decimal point. Next, the mass of my rocket, including the fuel, in metric tons. According to this, the fuel mass was 433.1 metric tons, listed there. So 433.1 metric tons. The percentage of thrust, that's your throttling. Let's suppose it's 100%, and we'll use that number. And your launch angle we'll use is 90 degrees, so that way you're launching straight up. And you'll see when you do that, that it will give you your thrust to weight ratio along with the initial acceleration in meters per second squared. And since the thrust to weight ratio is greater than 1, you achieve liftoff. Okay? You'll notice that if I change the angle, those numbers will change as well. Let's say it was 45 degrees. Okay, I got a thrust to weight ratio of about 3.8. Let's say it was 30 degrees, 2.6. It was 20 degrees, we're getting a little bit lower, 10 degrees. And you'll notice that if I were to launch it at an angle of 10 degrees from the vertical to the vertical, I would not successfully be able to launch. Not enough of the thrust is going upward. So at about 11 degrees, just barely makes it. So minimum launch angle would be at an 11 degree angle, but 90 is what you really want there. All right, you'll also notice that, as pointed out down here, there are a variety of additional tabs that we'll be accessing, maybe not all of them, but some of them certainly during the course of the semester as we perform more sophisticated calculations on rocket launches with more sophisticated math. But I wanted to show this to you and how you use it. Again, choose a different rocket than the Falcon Heavy, because I've already shown you that one. You can choose the Starship that SpaceX is doing, or the Shepard one, I think is what Blue Origin's rocket name is called. Or you can use a space shuttle, or a Russian rocket, or a Chinese rocket, or a European rocket. I believe the Japanese have their own rockets as well. Perhaps India and a few other nations have their own. If you want to choose a less commonly considered rocket, but find the mass, find the thrust of the first stage, determine what the thrust to weight ratio is in the initial acceleration. All right. So with that, we'll conclude this lecture on rocket basics. And I also want to remind everyone that the model rockets are now available at the bookstore. If you pre-ordered and paid for it, you just have to show up. They are open Tuesday, Wednesday, Thursday. Tuesday's already pretty much out, from 10 a.m. to 5 p.m. And you want to get the rocket before 5 o'clock on Thursday, so that way you will be able to construct it over the weekend. And I will post a subsequent video this week on putting together this particular rocket, as well as an additional video on another one of the topics we were covering this week. Let me see if I can bring that up. Here we go. So week 2, we did learning to work with others. That was what we did in class on Monday. So there'll be another video on academic writing and speaking later on this week. All right. So that concludes this video on Rocket Basics.